Yes, thanks very much. So we'll continue where I stopped this morning. And essentially, I want to show you why you get a fluctuation-induced first-order transition when your mean field theory predicts a continuous one. So the notes will be available online. I will not do the derivation of the mean field equation, but that's pretty standard and it's done in the note. So I'll just start from them. I wrote them this morning. And I will work in 1D because it's easier. It doesn't change anything. It changes the fact that there would not be a transition anyway, but for what I will be discussing, it doesn't change anything. So you have the dynamics of the density field, which is doing diffusive relaxation and is advected by the magnetization. And the dynamics of the magnetization field is also relaxing. There is this advection by density, which is a bit weird, but that's, that can be understood pretty easily. And then I have my alignment term, where f of rho m, I will take it to be alpha rho minus gamma rho cube over m square. No, sorry, gamma m cube over rho square. And this would be my mean field equation. And what I told you this morning is that if alpha is a constant, it predicts a continuous transition. And what I want to see is what happens if I add a small noise. I assume there is a tube, yeah. Because my magnetization is the sum of rho spin, I expect that its fluctuation scale as root rho. And what I want to do is to see what happens when I turn on sigma. So if I have sigma equals 0, I have my mean field solutions to this PD, which I can call rho naught of xt and m naught of xt. And the question is, if I take sigma positive but small, and I look at rho tilde, which is the average of rho of xt, and m tilde, which is the average of m of xt, can I build deterministic equation for this field? So can I build a renormalized evolution equation? And what will happen? Okay? So when I have linear terms like here, if I just take the average, I get the average, everything's fine. If I take the average of the noise, I do Ito, so it's 0. But here I have a nonlinear function, in particular here, and so this average here is what you have to compute, and the fluctuations will renormalize it. Morally, what I want to do is I want to take the average of this guy and write it as a function of the average. So how can you do that? The idea is to say that if my noise is small, rho will be close to rho naught. Okay, and so I want to try an expansion in which I write rho equal rho naught plus root sigma rho 1 plus sigma rho 2 plus higher order, and m equal m naught plus root sigma m1 plus sigma m2. Why am I using this scaling? Because I know the answer and I know it works. If I didn't know, I would try general scaling and I would try to find one that works. Yes?
So the noise here was put in phenomenologically?
Yes.
So why do you put it only in the M field?
I can also put it in the rho field. It just makes things more complicated. But I can have it on both sides.
The root rho just comes from like
the root rho, the root rho is a central limit theorem scaling. That's just saying, I have many spins that I'm summing. That's what I expect to be the case. And you can check numerically that it works fine for small fluctuations. Yeah. Any other question about the model or what I want to do? Yes?
Do you translate non-multiplicative noise? Does it work, right?
I will. So I will get an answer. Okay. So when I do my computation, what will happen is that I will renormalize these coefficients, okay? And you'll see that the renormalization depends on this amplitude. So the renormalization will change. And we can discuss the consequence of taking other time of noise maybe when we have the formula in front of us. Okay? Any other question? I can just tell you that if you make a simulation of the active Ising model and you measure the fluctuations, that's the scaling you should get for this model. There could be other model in which another scaling would be good. Okay. So how do we proceed? We have our equations, 1 and 2, and we want to derive equations order by order for rho. And so essentially what we do is we inject these and that's into this equation, and we look order by order at what happens. So if I look at order sigma to the power 0, well, what I have is just the mean field equations. So that's not very interesting, but you can do it. And things become more interesting when I look at first order and second order. So the leading non-trivial order is root epsilon. So to have root epsilon in these linear terms, what I will get is just rho 1. And when I have these terms here, these are nonlinear functions of rho. So what I do is I Taylor expand them around rho equal rho naught. And the first order, and the zeroth order here will give me in terms of order root sigma. And the first order there will give me in terms of root sigma because of this. So what I get for rho 1 is dt of rho 1 is d dxx rho 1 minus v dx m1. And if I look at the dynamics for m1, dt of m1, the linear term, they are trivial, dxx m1 minus v dx rho 1. And here I will have, okay, first I will write it complicated way, rho 1 minus df over d rho at rho naught m naught, so that it's an m, times m1, and then I get plus root 2 rho naught eta. Okay? So that's the dynamics I get at order root sigma. Unfortunately, I will also need the order sigma to go forward, so I can continue. For the order sigma, the linear part is the same. I get dt rho 2 is d dxx rho 2 minus v dx m2, and dt m2 is d dxx m2 minus v dx rho 2. And then in this term, I have to ask myself, what is of order sigma? So if I look at the first, okay, why aren't you working? Okay, so if I look at the first order derivative of this guy close to rho naught m naught, I will have df over d rho times rho minus rho naught, so root sigma sigma 1, that's what gave me this. And then I have sigma rho 2, so that's the first contribution, the second derivative of this guy times rho 2. But if I were to keep on the next order, I would have, for instance, 1/2 of df over d rho square times rho minus rho naught square. And you see that rho minus rho naught square will get a rho 1 square. So I have a bit more terms here. I will have, let me check that I don't do anything wrong. Yeah. I will have, and now I write it in a more concise way, df rho 2 minus dm f m2, and then I have minus 1/2 of d rho f rho 1 square minus 1/2 dm m f times m1 square, and then I get minus d rho m f times m1 rho 1. And I will need to have the first order derivative of the noise, so I get plus rho 1 over root 2 rho 0 eta. Okay, so that's my terms to order sigma. Now, what I want to construct is the dynamics for average for rho tilde. And rho tilde, you see that if I replace rho by its expression, I get the average of rho naught plus root sigma rho 1 plus sigma rho 2. So I can just take these equations, sum them, I mean multiply this one by root sigma, this one by sigma, and sum the three of them, and I would get an equation for the average density field rho tilde. So let's do it. So we do the sum over I of sigma to the power I over 2 times dt rho I, from I equals 0, I equals 0 to 2. And what we get is dt rho tilde. This one is linear, so it's trivial. We get dxx rho tilde minus v dx m tilde. The one that's more interesting is what happened with the magnetization. The linear part is simple. I get dt m tilde, d dxx m tilde minus v dx rho tilde. And then I have a bunch of terms that have to sum. Okay? So at order 0, I have no contribution, but the d rho f, you see it enters at both orders, so we'll get at order 0, I get the mean field term, f rho naught m naught. And then I have my order 1 contribution, which is here, so plus, so d rho f, and d rho f has root sigma rho 1, but it also has sigma rho 2. Sigma rho 2. Then there is dmf, which has root sigma m1 plus sigma m2. And then I have this second order derivative in addition, which is plus sigma over 2 d rho f rho 1 square plus sigma over 2 d mf m1 square plus sigma d rho m m1 rho 1. And that's it. And because I've taken the average, which I forgot to write, the average of the noise gives me 0. So I'm kind of happy because this is a closed equation for rho tilde and m tilde. That starts good, and here things go bad, right? Because I don't have something which is closed. I would have been happy if I had f of rho tilde m tilde, which are the average field, and instead I have f of rho naught m naught, which are the mean field. And mean field and average field are not the same. But that's okay, because they're close to each other. So what I can say is that f of rho tilde m tilde is f of rho naught m naught plus some terms. I can Taylor expand again. So I Taylor expand. I say that f of rho tilde m tilde is f of rho naught plus root sigma average. So it's f of average of rho, so average rho 1 plus sigma average rho 2. And then I get m naught plus root sigma average m1 plus sigma average m2. Okay? By definition, sigma is small, so I can Taylor expand this guy. And I get f of rho naught m naught. Then my first order correction, then I will have d rho f times root sigma average, and I forgot some averages. This was an average, so I should have average here. Sorry, let me put them back. So this was the average field, so I have average signs here, 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 and most importantly, around the squares and the double product. So if I look at my first order, it will be exactly the same as above. Average rho 2 plus dmf times root sigma average m1 plus sigma average m2. But what's interesting is that now when I look at the second order derivative, I will get rho tilde minus rho naught. So I will get this guy square. And so instead of having the average of the square field, I would get the square of the average field. So I will get plus, plus sigma over 2 d rho rho of f times average of rho 1 square plus sigma over 2 d m f average of m1 square plus sigma d rho m f average of rho 1 m1. So if I want to close my equation here and to get rid of this f of rho naught m naught, I can use this expression for f of rho naught m naught. I can take everything that's on the right here, put it on the other hand, and I'll say that f of rho naught m naught is f of rho hat m hat minus all these terms. So you see that the linear terms, they will exactly cancel this one. And the nonlinear terms, I will get average of rho 1 square minus average of rho 1 square. So I will get the connected, the two-point function, the connected two-point function. And so what I get as a result is that dt of m tilde is d dxx m tilde minus v dx rho tilde minus f of rho tilde m tilde. So I'm happy about that. And then the linear terms disappear, and I'm left with minus sigma over 2 d rho f times average of rho 1 square connected minus sigma over 2 dmm f times average of m1 connected minus sigma d rho m f average of rho 1 m1 connected. Okay. So this is my rho normalized dynamics for the field M to order sigma. Of course, now these f here that were before evaluated at rho naught m naught, they are now evaluated at rho tilde m tilde because the difference is higher order in sigma, so I'm fine with that. One of the problems is that I don't know what are these correlators, and so I have to solve them. And to solve them, I need to know rho 1 and m1. So what I have to do is I have to go back and look at the dynamics of rho 1 and m1 and see if I can do something with it. But when you look at this, you see it's fine. Because this is a linear problem for rho 1 and m1. So it's just a set of coupled linear Langevin equation. And so actually you can use this system to compute this correlator and close the equation. So I'll show you how you do it. You can do it analytically explicitly in a homogeneous system. So for a homogeneous system, this is a set of linear PDEs with constant coefficient. So you can just Fourier transform them. And then you use Parseval-Porcherel to compute this correlator as the integral of rho q, rho minus q, mq, m minus q, and rho q, m minus q. And then you can compute the cumulants. When you do that, the result is as follows. you get a closed system on equation, which is dt rho is dt rho tilde is d Laplacian rho tilde minus v dx m tilde, and dx m tilde is d dxx m tilde minus v dx rho tilde, and you get a renormalized coefficient minus alpha tilde m tilde and minus gamma hat m tilde cube over rho tilde square, where you can compute the expression of these coefficients. So what you find is that alpha hat is alpha, the unrenormalized coefficient, plus 3 sigma gamma over 2v times rho tilde. And then there is a scaling function, which is dimension 3 over 2 plus u, with u a dimensionless parameter that does not depend on density. And gamma tilde is gamma plus something which is order sigma that you can compute, but it's unimportant in what we discuss. And so what you see is that what I had argued unwavingly before lunch, that the critical temperature is mean field only at infinite density, and that at finite density you should get 1 over rho corrections. You can compute it analytically, and you can get the expression of these corrections to leading order in 1 over rho tilde. And if you compare with numerical simulation, it works very well. Now we can go back to your question. I can rewrite this as sigma rho tilde over rho tilde square. If I had done additive noise, that would have been this. I still have a correction, it's just higher order. You could say, oh, but if instead I say that sigma is proportional to rho tilde, then these order cancel, and you would say there is no density-dependent correction. It's true, but then you would get it to higher order in the perturbation theory. So whatever amplitude we put in the noise, we always get this density-dependent renormalization. The one that we can compute easily is like that. You can also do some field theoretical treatment and compute this renormalization not in the noise amplitude, but in gamma, in the strength of the nonlinearity, and you get something that's consistent to leading order. Okay, so yes.
Maybe one quick question. So to do that, you need some kind of stability of your equation to do the perturbation.
Yes.
On the other hand, you want to apply that at the critical point, and so.
Okay, very good. Yeah, very good catch. So here, the assumption I'm doing is that my noise is very small, so that my mean field equation is very close to my average solution is very close to the mean field solution. And on the other hand, what I'm getting as a result is that my transition threshold is renormalized. And so the mean field equation is stable longer than the renormalized equation. And so these work very well away from the transition, very deep in the ordered phase. And when you get close to the transition, because of the instability of, because the mass vanishes, the mean field mass vanishes, then it gets harder and harder. So it's a perturbation that works well away from the transition, but not close to the transition.
You could hope to have maybe the phase separation line, but not the exponent, or there could be some further correction in the exponent or things like that.
Yes.
To the instabilities.
Yes. So okay. So it's complicated to know what transition precisely you're talking about. So let me just draw back the phase diagram and try to be a bit more precise about what I say we claim we've achieved. So our mean field theory is that T mean field qual 1 is here. And what this computation tells us is that actually fluctuations stabilize order. And so there is a correction where T is actually T mean field minus something like R over rho. And so the computation that we work is fine coming this way or coming that way, but they will fail between these two lines. Okay? So if you go in the, so this is what we derive in the high temperature phase coming down. You could also do it in the low temperature phase, starting from an ordered phase and going up. And you get different corrections for the mass on both sides. What matters here is that when you go down, mean field tells you you should become unstable here, and this tells you you'll become unstable after. However, when you go to this white line, the dynamics for rho naught and m naught becomes linearly unstable, and so your perturbation theory doesn't work anymore because the Hessian is the wrong side and everything. So essentially, this is the region where this is working. Are they other questions? And so one of the reasons why I wanted to do that on the board is that this method, you can apply it to kind of tons of different PDEs. So it's something we do it here, but if you have another model that you like, where you want to know how the noise renormalizes the coefficients, you can do that. As you see, we get the renormalization of the coefficients which do not have gradients in front of them, and that's because we do it in a homogeneous system. You can also do it for profiles that are not homogeneous, but it's much harder. You have to use dynamical action, and this is much more complicated than this. Yes?
Sorry, Julien. So one is tempted to write F tilde, big F tilde there, but the sign of alpha hat in the original alpha is different.
It shouldn't.
You see
yeah, but it's minus F and alpha, and F was plus alpha.
And then here is minus alpha hat minus gamma.
Yeah, so it's consistent, right? If I replace F by this guy, I would get minus. Oh, you're saying that this sign is wrong. Yeah.
So this, yeah.
Okay, sorry. So yeah. The sign of alpha is fine, but this sign was wrong. Thanks. Yeah.
Yes.
Yeah. Okay. Yes.
Just a small question. So in this box equation, you have these cumulants. They're the two-point function valued at the same point. Like, aren't you going to get like a delta of 0 or something when you evaluate that, or?
So so you will get the integral of delta rho q, delta rho minus q that you can do, which is finite. So no is the answer. But I see what you're saying, and I think that no, and that's because you have a mass. You're thinking about a case where you don't have a mass, and then you have a divergence for this integral. And that's exactly what happens when you get close to this line. So essentially, if you one case which is trivial to do, which I didn't have the time to do, is if you try to do this computation for the linear terms, so you take the boxed equation and you put v to 0. And then you can do it, and what you get for the correlator is the integral over q square plus m square, and you get just pi for this integral, for the perfector.
And then the other thing is that so sigma here has your expansion parameter has units of inverse time, right? So rho 1, rho naught, rho 2 all have different dimensions. The way you set it up.
Could be. Finish the question. You can do it in a dimensionless form. I don't think that this is a big problem.
I'm just wondering what's the actual small parameter, because I can rescale my units of time and make sigma as small as I want. So sigma has to be small compared to what? Here.
This is a good question. I mean, you can dimensionalize the equation. It would be the noise amplitude. I think for some reason I prefer to see this as a large rho expansion as a small sigma. And I think it's the same thing. And probably once you dimensionalize it, that's what it ends up being. So I would rescale time, rescale space, and rescale the rho by rho naught. And then make a large expansion. I don't know. I've dimensionalized them, so I cannot tell you. That's a good question. Any other question? Okay, so let's switch back to the slide. Oh, yeah. Did I turn it on or off? Oh, that was March. Yeah. Who? No, tableau. Yes. Sorry. Okay. Okay, good. That's a good pointer. Okay, so this is the same thing in one slide. You start from your equation. You want to compute the average. In the small noise limits, you take you expand with these parameters. You get your mean field equation plus some correlators to compute. You need to compute this guy to leading order in sigma. To do that, you take the linear system, you solve into Fourier space, you do this integral, which are finite, and you get a renormalized Landau term with this new term. And this is the renormalization of the mass that you get. And you see that this renormalization is both linear in the noise amplitude and as 1 over rho naught. And so fluctuations make the mass depend on density. Of course, you could tell me you worked in 1D, you made an expansion, this was Gaussian, lots of approximations. How do we know this is true? And the answer is that, well, if you don't believe me, you can take this equation with a deterministic part that predicts a continuous transition, and you plug it in a computer. And if you do that, you can look at the phase diagram, and you can compare, for instance, the average norm of the order parameter compared to the mean field. So the green line here is the mean field solution without noise. You simulate your stochastic PD in 2D, and you get the blue points. So you see the first thing is that there is a shift of the onset of order, which means that you have to go lower in temperature to get order. So that's compatible with the fact that alpha tilde is larger than alpha. But in addition, if you look at the 3 black points here, the result of simulation would show you bands. So this is the magnetization, which is 0 and then order. This is the density field, and that's a snapshot. And so in this PDE, whose deterministic part is mean field and does not accept band solution, you get, when you simulate the stochastic PDE, band solutions, which you can understand because of the normalization of the mass. So yes, it works fine. One of the things which is nice is that I wrote this here, but you could do it for very general function, and so this is very generic, and it tells you that all the scaling limits that people have studied, which give you second order phase transition, continuous transition, for instance the one by Degon or others, they are singular limits. They're well-defined limits that are interesting, but if you step away from them, you get a different physics. Much like our activizing model that I wanted to do mean field is not mean field, and it's dangerously not mean field. Okay, so of course, once we got that result, we were very happy, and then Irene Giardina was in the PhD committee of David Martin, and then she said, okay, you have this for metric model, but surely for topological model it must not work. So we said, okay, let's try to see what happens. So what are topological models? That are these systems in which instead of aligning with your nearest neighbors, instead of aligning with all neighbors within a given distance, you align, for instance, with nearest neighbors, or you align with Voronoi neighbors. And indeed, in the literature, most results were claiming that the transition was continuous. So we struggled a bit about how to adapt our formalism to this case. And we decided to kind of try and build a field theory for a topological model. So how do we do that? We assume that our particles at position R, they align with a field m hat of R, which results from a topological construction. So for instance, if we want to get the k nearest neighbors, we say that the interaction range depends on where you are. And your interaction range y of x is such that when you integrate from x minus y of x to x plus y of x, the density field, you get exactly k. So if you dilute, your long range. If you're dense, your short range. But you always have the same number of neighbors. And then how do you define the field with which you align? Well, it's simply then 1 over the number of neighbors times the total magnetization in this field. You can derive the Landau term with which you would align in this case. And you should note that in this F term, now you have these M and rho here that are counting statistics. They come from the fact that the number of plus spins is rho plus M divided by 2, the number of minus spins is rho minus M divided by 2. While in the hyperbolic cosine and hyperbolic sine, you have these M hat, which are the field with which you align, which does not have to be the same thing. So the Landau term by alpha, these terms here, which is very simple because the M with which you align is the same as the local M, here is more complicated because you both have an M which is a counting statistics and an M which is the field which you align. you can build the mean-field hydrodynamics corresponding to this model, and it predicts a continuous transition at mean-field level in agreement with the literature. Then you can ask David.
Julien,
yes.
But K is maybe 3 or 5
4 or 6,
and but you
or 17.2
or 17.2, maybe 17 or 18, I say. But you have a continuous equation. So a priori, the birds they would see really, I mean, some microscopic structure, and you do the approximation by some.
Yes, it's a model. You can criticize this model. It's a model in which it's true. It's the only way we could think about making a topological field theory. You know, what's the closest you can do? Okay, and indeed, it's not a perfect one. If you replace this by delta function, it works fine. That's the. So this would pick exactly, the right magnetization in this case. Okay, so again, we take our mean field model, which this time has lost any connection with microscopics. We complement it with noise, and after lots of effort from David, you can indeed compute the renormalized coefficient, and again, you predict a fluctuation-induced first-order transition. So we're happy, but can we prove that this is true? So we take an off-lattice Ising model. So you have your particles which move left or right. So if the speed is, if SI is 1, you go to the right. If SI is -1, you go to the left. You have some diffusion. The spin can flip at some rate given by terms that satisfy this detailed balance with the right Hamiltonian. And this time you see, Amer, we use your mi hat, which is, okay, oh, still, no, sorry, forget about what I said. There's still 1/k. So it's still the average magnetization over your neighbors. And this time, instead of being always in a distance, it's just your k nearest neighbors. And if you simulate that, you see that, okay, the mean field transition is here. Not only do you again have this crescent shape that tells you that your onset has been, is become density dependent, but when you simulate really, really big system, you do see bands which are traveling. It took 3 more years for John Marco Spera to get the same band in Voronoi models, because once we got them in the k nearest neighbors model, people told us, but surely in the Voronoi model you won't get them. So we got them for active Ising model. We failed for Vicek, and Daniel Sussman, developed a crazy code on GPU, and last year he got the bands also for the Voronoi Vicek model. So now I think that it is solid, and we can say that fluctuations generically make critical temperatures depend on density. This leads to a phase separation scenario instead of a continuous transition. It holds for metric and topological model. And you can look at these papers if you want to know more about that. Now, everything I've been telling you since I started this course on collective motion was motivated by the Vicek model and developed for the active Ising model. And different symmetries of order parameter, you could question whether this is actually relevant for Flocking's models with factorial order parameter. And so in collaboration with Hugues Chaté, we went back to the Vicek model, and we looked again at the phase diagram that you see here, which again has the same crescent shape with the same 3 phases. And there is indeed a difference between the active Ising model and the Vicek model. In the active Ising model, what you have is phase separation. So if I'm in this state, in the band here, and I increase the density, I go from a small band to a wide band. If I do the same in the Vicek model, I increase the number of bands. And you can test that, so you could maybe say that this is a kind of a transient, and yes. So you can, this is a simulation of the Vicek model. You start from phase separated, and you wait, and you wait, and you wait, and initially it looks like this is robust and stable and macroscopically phase separated. And then at some point you start to see these big gaps here that fluctuate. Okay, not big enough, but let's wait. Really, really big gaps. And now if you make this go forward, you see that these gaps percolate and now have 3 bands. Right. And I can let my simulation run and speed up the simulation, because this is a crazy long simulation. And you see that you relax to this smectic organization of bands. And so this is really the asymptotic state. And I think that Hugues made also crazy large simulation on Chinese supercomputer. So you take a very big system and you see this relaxation to these equally spaced bands. Okay, so that's a difference. Are there other differences? So one thing which is important is that you can compare the profile of this band as you crank up the size of the system or increase the density. And here we compare a system with 2 bands or a system with 6 bands, and you see that they overlap perfectly. So there is a well-defined band profile that the system selects for that survives in the thermodynamic limit. You could ask, is it still a liquid-gas-like transition? So before, what we were doing to check that, we were increasing density and observing that the fraction of liquid scales linearly. What we can do here is we can measure the number of bands in the system as function of the distance between the gas density and the average density. And you see that for 2 different noise, you have different slopes, but this is linear. So again, you have the same scaling. Okay, so you can keep on looking for all the parameters that we like in the liquid-gas transition, and one of the reasons why Vicek and coworkers thought that the transition was critical is this plot. So because people believe this was a ferromagnetic transition, what they looked at was the average magnetization per spin. So you take 1 over L times the sum over I of the vectors of spin I, that's your polarization, and you plot the polarization versus rho minus rho gas. And you see something that looks like this square root Ising-like function, and that's not one of these nice linear scaling that I predicted. However, this is also not the fraction of the liquid phase. So if I want the fraction of the liquid phase, what I would do is I would have to sum the magnetization and divide by L square, not by N. Between the two of them, you have a factor of rho. And so actually, if instead you plot this order parameter instead of that order parameter, you recover a perfectly nice scaling. And these different lines are different system size. And so again, the finite size scaling of this transition is again consistent with the liquid-gas transition. You can show that in your system you can have either spindle decomposition or nucleation, depending on where you make a quench. So this, you see, initially you don't see much, you don't see much, you don't see much, and then at some point, after a long time, you see some kind of, it's not a droplet, it's a bandlet that kind of forms and then coarsen. So that would be typical of a nucleation regime, right? So that's when you put the system close to the binodal but out of the spinodal. And if you do instead a quench deep in the coexistence phase, as soon as you start the simulation, you see order everywhere and very rapidly, and then you have a different type of coarsening process, which would still lead to the global phase. So that's for a standard signature again of liquid-gas phase transition. You asked about this first order versus not first order transition. When you look at the liquid-gas transition, you go from a gas by increasing the density at some point. You get the smallest stable droplet you can have, and then your droplet grows. So when you nucleate this droplet, you get a discontinuity of your order parameter, if your order parameter is liquid fraction, but only in a finite system. Because if I look at the liquid fraction of this system when I send L to infinity, the critical radius of my droplets goes to 0. And so in bigger and bigger system, if I plot the fraction, the magnetization or the fraction of liquid at the onset, I should be able to get closer and closer to 0. And indeed, you have the gas binodal here. And you see as we increase the system size and we come from the bend phase, we are able to go closer and closer to 0. So in the asymptotic limit, what we would get is a straight line that would go here and then bend there. Again, that's consistent with what happens in the liquid-gas phase separation. If you try to do the standard finite size scaling you do for ferromagnetic transition, you would go for Binder cumulants. Your first order Binder cumulant would have a negative peak because of this discontinuity. So initially, very small system, you'd see something continuous. Then you would see a negative peak. And as you keep increasing the system, the peak becomes less and less negative, completely confusing. And again, you have hysteresis loops if you loop through the density up and down close to the gas binodal. You can look at the order parameter, and again, you have hysteresis. Near the liquid binodal, because you have bands, it's harder. So what you can do is the variance of the density, and again, you can show that there is a hysteresis loop. So again, all standard signatures of the liquid gas are okay, except that the nature of the band is very different. And of course, it's not a small issue. Okay? The fact that we have these two systems and we change order parameter and suddenly we have completely different types of flux is important. And if you think about birds, the most important thing that you want to understand about birds is the shape they have in the sky. So whether it's finite or microscopic is important. And so this was a kind of outstanding problem, and we wanted to understand whether we can predict the shape of this flock. So the natural explanation, if you come from nonlinear mechanics, is to say, well, I have hydrodynamic equations, one for my Vicek model, one for my Ising model. I will build the hydrodynamic equation. I will look for the propagative solution. One will accept trains of solitons, periodic bands, and the other one will accept phase-separated solution. So let's see how this goes. So we have our model for the active Ising model, in which we've used that the transition is density dependent, the mass. Sorry for the change of letter. And if I look at the paper by Eric Bertin for the Vicek model, they have something a bit different. So they don't have this diffusion term here on the density. The advection by the magnetization is in all directions, not just along X. And then to second order ingredient, we don't have much in this system, but here they have a whole bunch of horrible nonlinearities. Okay, so apparently very different equations. So it would make sense that they accept different type of propagative solution. So the question is how can we look for them? And I will refer to the Ising model as the scalar case and the Vicek model as the vectorial case. Okay? So how do we look for propagative solution? Again, that's a piece of mathematics, which use again the Newton mapping that I used yesterday. So the first thing we do is we say, well, we want a traveling band. So we look for solutions which are steady state in a co-moving frame. So we look for m of xt. We'll just look at some orientation, something that's oriented along x and 0 along y, but that doesn't make any difference. And then our field rho of xt will depend through x and t only through x minus ct. And so when we make these ansatz, we have a first unknown, which is our speed c, much like we had an unknown mu when we were looking for our phase coexistence. Okay? So dt rho will become minus c, the derivative of rho with respect to its argument, which I will call a prime. So I get minus c rho prime is minus v m prime, which is minus v grad m. And then the dynamics on m becomes minus cm prime, and then I have my diffusion, and I'm doing this for the vectorial case first. I have these mm prime terms that comes from the nonlinearities. I get a rho prime, and I get these cubic Landau term. Okay? So how do I make progress? I notice that the first one are two constants times two derivatives, so I can integrate these immediately. And I can solve it, and I can say that rho, so I can integrate it between the gas phase and the liquid phase. Okay, so I'm looking for a solution in which maybe I have something like that. Okay, so here I have my gas density, and what I know is that in the gas density the magnetization is 0, and then it goes elsewhere. So if I integrate this equation from the gas phase to the liquid phase, or to any point, I get that rho of x is rho g plus v over c m minus m gas, but m gas being 0, I just get m. So then I have another unknown, rho g, that I don't know, but I can take this and inject it in this equation. Okay? Because this is a bit complicated, it's nonlinear, I can linearize it, it makes things easier, but I could also try to solve it like that, it doesn't make a big difference. And I get an equation that looks like this. So I get second order derivative plus, so that would be like mass times acceleration, like a friction times the speed, and then something local in m, like a potential. The difference with respect to the case of MIPS is that in MIPS I just had one unknown, which was the chemical potential mu, and here I have two unknowns, C and rho gas. So I have to find values of C and rho gas for which I can get stable solution, then check that they are linearly stable, and then I will understand everything. So this is for the vectorial case, and we see how it looks like. Now let's see how different it is when we look at the scalar case. Okay? So the scalar case is a bit more complicated because I have this D Laplacian rho. But I can solve this perturbatively, and to leading order in gradients, what I get this time is rho gas plus V over Cm, that's the same as before, and this term here adds a new term there. Okay? Yes?
Could you explain why the previous slide wasn't underdetermined with two?
Yes, there is one that's by ansatz, C, I don't know what it is, and then this equation here, when I integrate it, there is an integration constant. I don't know rho gas. And so then I inject this in this guy, and I get an equation which has two unknowns, rho gas and C.
But in the previous Newton mapping, there was only mu in the final.
Because it was for a single scalar equation. So here, to go from two equations to one, there is one unknown that I don't know that I have to add.
Okay.
Mathematically, it's how it counts. There was another question? No. Yes?
I mean, in the MIPS case, C equals 0. You would still have it, but it's 0 because you have no
yes,
more
you could say that also. You look for static.
If you want this to be consistent with one another.
And mu and rho g are different things, but yeah, in most cases you have something that you don't need.
Have you, a posteriori, have you put band speed as C and see what you get?
Yeah, we'll get there. So,
Okay.
Okay, so the scalar case, again, you did that, you inject it here, you look at what it happened, and same thing. Okay, mass a bit different, but same form. Mass times acceleration, again a nonlinear damping, and again a potential. So the two different equations, vectorial and scalar, have exactly the same form. Okay, so let's still look at whether they accept propagative solution. So essentially the form of this system is, so it's a Newton equation of motion for a particle of mass d, position m, speed m prime, and we can introduce a potential v of m, taking this cubic here. And we have a nonlinear friction that changes sign, so there is a point somewhere where the friction goes from positive to negative. And when we are looking at a trajectory like that, we are looking at a periodic orbit, right? I start here, I go there, and then I come back. So the question is, all my parameters v of m, a0, a1, they depend on c and rho g. Can I adapt the value in c and rho g such that I find a solution that give me a propagative solution like that? Okay, so let's look at the type of solution we can get. So the answer is yes, there are a bunch of solutions. First type of solution you can get is plotted here. So for these particular values of c and rho gas, if you start here, you'll go down, come back, come back, come back. You get periodic orbit. And if you plot in space what this corresponds to, it corresponds to a train of band. These are your Witschek bands. Good. Now, what I can do is I can change a little bit the parameters such that this point here gets closer to this critical point here. And then essentially the limiting case is when these reach exactly the critical point, and then I have a homoclinic solution, meaning something that starts from a critical point, goes down, comes back, and essentially it's an isolated soliton. So when I go from here to there, what happens is the distance between this band increases until at the end I have a single band in my domain. Okay? That's a limiting case of the Witschek case. But then what happens is that in my potential I have a second critical point. So I can keep changing my parameter, and now this band can widen until I don't get an homoclinic solution, but an heteroclinic solution. I start in this point, spend an infinite time there, falls down, goes there, spend an infinite time there, falls down, go there. And this is macroscopic phase separation. And so the take-home message is that my vectorial and scalar harmonic equations accept both the periodic solutions of Witschek and the phase-separated solution of Witschek. Both are linearly stable. You put them in a computer, you can check that they have finite Baselian attractions. And what you get in the PDE only depends on initial condition. So for instance, here, I'm simulating the scalar PDE of Ising, and I get a perfectly nice microphase separation. And here I'm spinning the vectorial PD of V check, and I get phase separation. So our initial intuition that nonlinear mechanics would give us the answer was wrong, and we can't distinguish between this system. So this was a bit worrying, and in particular, it could be that what determines where you end up is not a macroscopic property; it's a microscopic detail. There is no universality, and that would be a disaster. And it turns out that no, the only thing you need is noise. Okay, so if you take your hydrodynamic equation and you complement them with either scalar noise in the scalar case or vectorial noise in the vector case, then when you simulate your PD, the noise will select only one type of simulation. So here, this is simulations in which we start from phase-separated system, and we run the system with either the scalar or the vectorial order parameter. And we look at whether, this is the steady state. So the solution is that the noise, this is robust to the noise, but this is not. I showed you at the beginning a simulation of the microscopic V-check model and how this happened. I can now show you what happens. No, I cannot apparently. How is it called? Movie band break. Let me see if I can find this guy. Yes, PD. Okay. Okay, so we start, that's the PD with the vectorial order parameter. We let it run. See that it looks a lot like the macroscopic simulations I showed you earlier with less noise. And again, of course, the timing to speed up the movie was not very great, but let's see, maybe I can do it like that. I think it's around 15,000. So as time goes forward, okay. Just here you see we've nucleated the hole, and then at 30,000 a second hole, then more holes, and once these holes are created, the stem has to relax towards this equally distance band. Okay, so can we understand what's going on? If we look for all solutions, all values of C and rho gas which admit solution, that's the phase diagram that we get. So these are the values of C that we have. This is the value of rho gas divided by the density at the transition. You see that you have a 2D space with periodic solutions. If you lower rho gas, you take out density, so you go towards solitonic solution. And the faster the solution, the wider it is, until it gets to the phase-separated state. So there is a very simple coarsening process. The bigger, the faster. The faster you are, the easier it is to catch up with people in front of you and to eat them. And you become even bigger. And you keep running like that. And so the natural endpoint of this coarsening process would be phase separation. However, you're stochastic. And because you're stochastic, you have fluctuations. And these fluctuations, when you're too big, can create gaps in the bands and break them. If you compare, so this is characterized by these giant fluctuations. So what are giant fluctuations? You take a box in your system, and you measure both the average number of box and the variance. And you compare the root mean square versus the average number of particles in the box. When you have active Ising model, you're here. You see Gaussian-like fluctuations. The scalar PD is the same. When you have the V-check model, you're there. The vectorial PD is the same. And so you have these much larger fluctuations that probably explain why it's easier to nucleate gaps. It would be very nice to be able to predict that analytically and to be able to say, well, if I'm changing the noise, the scaling of my fluctuations are such that with probability 1, I create a gap versus not. But that we don't know how to do it. Okay, I don't know why this is not working anymore, but okay. So let me summarize what I told you so far. The liquid-gas transition, so the transition to collective motion is a liquid-gas transition in the canonical ensemble. Gas and liquid have different symmetries, and that has a strong consequence of the shape of the phase diagram. This is very robust. If you go in other models, you'll see the same thing. And I've discussed two universality classes. The first one is this active Ising class, in which you have a discrete symmetry for the order parameter, and you observe macroscopic phase separation. The second one is this active XY class, in which you have a continuous symmetry, and you observe microphase separation. And the way we understand the difference between the two is due to these fluctuations. Experimentally, there are evidence for the two classes. So the experiments by Denis Barthelot, which I already showed you, so I'm not going to show them again. Even though this system, you would imagine, is isotropic, it's not, because it's strongly confined. And what I will tell you on the next slide is one thing we've showed is if you take a model with a continuous order parameter and you discretize the angle, so you look at what's called the clock model, then as soon as you've discretized the angular degree of freedom, you fall back to the active Ising class, and this is probably why they have these very large bands which are stable. And these are experiments by Andreas Bausch on self-actin filaments, and instead they see these very clear finite width bands, which are of course very wiggly and everything, but that's more reminiscent of the active XY class. Okay, so this is something I discussed already earlier. Maybe I should be a bit more fair to the pre-existing literature. So if you look at the history of the literature of these flocking models, we know that in equilibrium, XY model, the long-range order is destroyed by spin wave. And so when people measured the long-range order in the V-check model, what they thought about was checking that the spin wave are not a problem. And so in a way that the Turner 2 ordered phase is stable against small fluctuations. Nobody thought about what happens when you have large fluctuations, because in equilibrium you have surface tension that helps you to deal with that. But for various reasons, both the group of Hugues-Châté and the group of Yariv-Kafri thought about looking at what happens in this case. Hugues had shown that if you have small obstacles or finite perturbations, you could destroy the order next to the coexistence region in the V-check model. And Yariv decided to test this stability of the active Ising model. And so he did this protocol that showed that your ordered phase, it's metastable and not globally stable. And so generically you'll break and you have these spontaneous reversals, which again are very hard to see. So how important it is in practice, it's an open question, but from a conceptual perspective, it's important. Also, for those of you who've looked at this model in 1D, when you try to simulate this in 1D, you get reversals. So you get a band that goes in one direction, and then you get small fluctuations ahead of the band, and it flips back and forth. And so in 1D, we know that we don't have an ordered phase, but this essentially mechanism is telling you that this extends in 2D, which was very surprising for us. There's still a lot of open questions. What are the other possible coexistence states? I've told you generically your ordered phase should be linearly unstable close to onset, but I've not told you generically where it should lead to. Already we've seen fully phase separated, microphase separated. Hugues look at a system with 4 aft asymmetric flocking where you align differently with people behind you and beyond you. And he has, instead of having bands whose number increase, he has bands that kind of diverge in height. Bands in Voronoi model were hard to see, but now they are seen. We don't know how robust the universality classes are, so we don't know what perturbations are relevant. There is a very nice work in equilibrium where you take XY model. I will never be able to do that, but I will try to draw it. And instead of having a spin that's continuous, you discretize it. You say that your spin can have a finite number of directions q. And so here q would be 8. And you ask what happens to your phase diagram. So you know that you would have some transition that would be your BKT transition, below which you would expect to have your BKT transition. When T is close to 0, when you have no temperature, your spins have really a lot of difficulty to fluctuate, and so they know that you're discrete, and there is a ferromagnetic phase. But at q equal 4, somewhere, there is a BKT phase which open here. So when you go down here, your system is in high temperature phase, then it believes it's like XY, and then it becomes ferromagnetic. So there is an interpolation in temperature. In active system, what happens is very different. What happens is that you have, let's say, 1 over q. So when 1 over q is 0, means q is infinite, it's xy. So here you have the xy physics. But as function of the system size, you will see something different. So if you have a small system, let me try to see. Here you have a V-check physics. But as the system increases, you always transition to active Ising model physics. And so whatever degree of anisotropy breaking you introduce in your model, you destroy the V-check phase, and instead you get active Ising universally class. Of course, I've given you one course about pairwise forces, one about alignment. Real systems have both of them. So we discussed briefly this active solidification in Quincke rollers, but I don't know if I have this movie here. But when you simulate particle-based system which have both pairwise forces and alignment, you get this crazy lava lamp type of dynamics in which, I don't even know how to start quantifying these kind of things, but you get cool movies. So, how can we understand this? Is there some form of universal theory that we can make in this regime? Then, I wanted to mention that the role of disorder is important, and for MIPS we now understand quite well how disorder should be put into the system, but in terms of collective motion, we don't know. And in experimental systems, the work by Denis Barthelot is for me really remarkable. I mean, it's the amazing system, very well controlled, that reproduces beautifully a phase transition. It's quite an achievement. But now we would like to do stuff with it. We could build materials that are self-propelled. We could. So I don't know if you've built these wooden construction when you were kids, but spreading glue is horrible. Could we make a self-spreading glue that would be passive? You bring some field, it becomes active. It instantaneously spreads. So I think that there are lots of applications that can be very interesting in doing that. Finally, I want to end by thanking you for your attention and all my collaborators. So the people in magenta are the people who were part of my group. And when doing this list, I realized that there is a very large number of people who ended up at Sorbonne University, so I need to keep this connection going. Colleagues at Université Paris-Cité, where I was before going to MIT, long-term collaborator, Mike Kate, Sukhshate, Yarif Kafri, and then a bunch of other people with whom I've collaborated on more specific projects. Thank you for your attention. And finally, we are early, so there is time for questions. Yes.
So you mentioned the difference due to the noise to go from the bands to the Ising structure, and but the instability. Yes, this one was right there. But I mean the instability you mentioned this morning.
Yes.
It's not noise related. It's something different.
So yeah, it's different. So the nucleation of the droplet, the reverse droplet, would be much faster in V-check model, but this reverse droplet is not stable in most of the phase diagram. So essentially, for the difficult part, I mean, this takes a lot of time, but it's not difficult. You need noise and you need to wait. And if you have an infinite system, it will always happen. What's difficult is this, having a small droplet of minority phase to grow. And what you need for this to happen is you need that as time goes on, these guys grows by, essentially here you have lots of non-believers who come and meet you, and you convert them, and they join your religion, and you go to the right. If you have a continuous order parameter at the front of the comet, you're looking right. But then as you go to the side, people look to the left, and they just go in another direction. And then when somebody comes pointing that way, the angle increases, and then these people can win. And so the growth of this droplet is what doesn't happen in the V-check model. It can happen, but only close to the onset. So there is a transverse instability that kills the domain wall. But indeed, you're right, and that's why we're very surprised of having been completely wrong on the activising model, but once we got these results, we were sure that things would be even worse in the V-check model, and we got wrong again, because actually we were looking at the wrong place. Any other question? Yes.
So this is kind of going back, but you showed that noise generates a row dependence in alpha. And
yes.
So another perspective is if you imagine approaching the transition from the homogeneous side, then you can expand this alpha.
You mean from the ordered phase?
No, from the disordered. Well.
Yes, so that's from the ordered phase. That's from the disordered phase.
Yes, yes. So I'm saying if you just expand alpha and rho, then you're just saying that noise is generating higher order terms allowed by symmetry, like because you can just expand this alpha, right?
Yes.
So I guess what I'm saying is, what I'm thinking is, what if you, instead of starting with this equation, you wrote down the most general theory allowed by symmetry? So and why didn't Toner 2 catch this? I mean, I don't know.
So why didn't Toner 2 catch MIPS? Why did nobody catch MIPS before we did the coarse graining? Because just phenomenological equations, it's easy to do in equilibrium, when the only thing you have to worry about is the free energy and then the mobility. Out of equilibrium, you just have much more. So I agree with you that if you could systematically be the most general equations, you would be sure to have all the phenomena in your equations. But then the result is that the equation you get is horrible. I mean, if you look at the GPhys 2009 by Eric Bertin, there is everything in this PDE to understand everything we did with the liquid gas phase separation. But the system is so complicated and the PDE is so horrible that you don't even know which term to look at. So sometimes simplicity is good. And so if you have a model and you coarse grain it, you're happy to have something that's minimal.
I guess here the problem is because it's like kind of okay, for example, who's to say that the next order correction isn't negative and then bringing the mass back down to a finite thing? I mean, so
fine, you need to kill the dependency to kill the. It's of course possible that in some case that happens. Now, maybe so as soon as alpha prime is non-zero, you get linear instability. So the condition is alpha prime non-zero, then you get a linear instability. Now there is to go in your direction. When we published that, people who are doing the topological case, they were happy. Because they're saying, we are topological. We don't care about densities. If we take this room and we double its size and we double the distance between each of us, our k-nearest neighbors don't change. We are insensitive to density. Of course, alpha should not depend on rho. This is true, but the fluctuations are still metric because we are moving. And so, for instance, the rate at which you change neighbor will be sensitive to density. And that way, this will be coming back. So it's very hard to know, has my model a symmetry that prevents an alpha of rho? You can say, well, if it's there, then you have a first order transition. Yes, but in practice, I'm not interested by things in principle. I'm interested in this experiment. And this experiment is showing me something. I want the specific coefficients. So it's a different type of perspective. And, Hohenberg-Halperin, amazingly powerful to classify critical phenomena in equilibrium. So far, phenomenological theory of active matter, not so successful, because just people keep missing terms. And when they get terms, they know the scale is not right. And so my own experience has been that deriving them from micro give us much more control. And the people who postulate things, so for instance, if you look at the equation of state for pressure, if you postulate it, there is no reason why it should be there. So let's not have it. And then you look at pairwise forces active particles, you build your field theory, boom, equation of state for pressure. So it's hard to know. And sometimes what's interesting is that something can be there or not when you have a given symmetry and you want to understand microscopically where it comes from. And if you think back towards equilibrium also, there is, I will close my answer with that. In equilibrium, you know that the large-scale physics of your system is a balance between energy and entropy. So you know what your microscopic tools are. You can play with things that change the entropy and things that play with the energy. It's maybe not trivial to see how they cross over scale, but that's the physics. Here you've got no clue. At the end of the day, what you want to do is engineer active systems. So you need to know how to relate the microscopic to macroscopic. And phenomenological theory will never tell you that. That's my last argument. Any other question? Yes.
So when your noise selects micro or macro phase separation, how does it depend on the amplitude of the noise that you?
As far as we can tell, it doesn't. The time will, but not the amplitude. We haven't looked at the functional form of the prefactor. I think we just put, it was additive noise in this case on the PD. So really the symmetry was
phenomenological.
Completely phenomenological, yeah. I don't think anyone has derived the noise for the flocking model in a controlled way. I don't know. Yeah, I don't know. I mean, there should be root row prefactor that I don't even know if we put them there. Here, the symmetry seems to be doing the job. And indeed, what I would like to do is people like Eric van den Eyden who have all these methods to look at reaction paths in non-equilibrium system to compute the time it takes to nucleate a gap in this band and the time it takes to nucleate a gap in this band. So one of the things I don't know is that when you look at the simulation, it looks like that when you have a gap that forms somewhere, it spreads deterministically afterwards. But it's super noisy, so it's hard to say. But it would be very interesting to know what is the reaction path that takes that nucleates these holes.
You need a proper noise.
You need a proper noise. I mean, already with this improper noise, I can ask the question because I see the difference, and then I can change the prefactor and see what happens. But yeah. Yes.
Sorry, do you consider any boundary condition, or you consider the infinite size for the simulation?
So far in everything we've done, almost. I mean, I showed you at some point closed boundary condition where the bands bounce back and forth. We've always used periodic boundary condition, and it's always the same idea that the walls are unimportant. You can send them to infinity, blah blah blah. And then we have a work with Mehran Kardar that was a bit worrying for us, because if you take a system that does MIPS, okay, like that, and you put walls, and you have perfectly smooth walls, then you're happy. If you're in equilibrium, what you can do is you can imagine that you put a random potential here, and a random potential there, and a random potential here. And then what you know is that you're adding boundary contribution to your free energy. So in the large system size limit, this is sub-extensive, so it doesn't matter. And in equilibrium, nothing would happen. In these active systems, this kills the phase separation. Instead of getting MIPS, you get a scale-free system with long-range correlation. And essentially, each of these small obstacles act as generating this long-range current. And this long-range current will steer the system and destroys it. So while we did not care too much about boundary condition for a long time, no, I think it was a big mistake. And indeed, it is important to look at these things. Experimentally, I'm not aware of systems where this has been seen. But definitely, playing with boundary condition is more important than we thought. Any other question?
Have you, well, not a question, but there's some papers on active Hamiltonian models where you couple velocities to spins.
Yes.
Is it truly active? We don't know, but the nice thing is that you can still have an equation of state, you can still define
Yes, so these are, I imagine you refer to works by Olivier Dauchot and Mathias Casvillis, Marco Tarzia and Letizia Cogliandolo. So one of the questions that they had was whether you can only get flocking in an active system or you could make an Hamiltonian dynamics. And so they have a very weird coupling between the momentum and the center of mass, and then they show that you can have phenomena which are not exactly like that but related. Yeah. I'm not sure what exactly is the conclusion of this, because you don't reproduce exactly these flocking systems, and I don't know how you would engineer that in practice. But as a proof of concept, it's if in your Hamiltonian you couple the orientation and the momentum is in a weird way, you can get this flocking state. I was a PhD committee of Matthias, but that was like 12 years ago, so I don't remember precisely but it was a cool system. It was a nice system. Yes.
So this noise, like then you get a certain alpha, whatever on this right, and the length scale at which you have the instability depends on this rho dependence. So does this noise correspond to, like, did you do some?
Okay. So this is you look at the value of alpha prime. So what you can do is you can do the linear stability of your system. What you find is Q equals 0 is always stable, and you have a finite Q instability. And you can look at how big should be your system such that there is at least one mode that's unstable, and it allows you to define a value L star. And you can look at how this L star varies with modulus of alpha prime, and that's the black line here. And these are simulations when we change the system size. So the system below the black line, they are too small to have unstable modes, and they're homogeneous. And the system above the black line, you see the bends. Of course, it's a log plot, so I'm not claiming that it's exact.
These are microscopic simulations, or?
These are simulations of the PDE with the noise and an alpha prime that we vary.
Did you also see something like with the microscopic simulations?
So the reason why we did that is because we were looking for so yes and no. We were looking for the bands in the Voronoi system, and let me see. Find this. Chaos neighbors. Okay. So this is activism model with Voronoi alignment. That's the best snapshot of a band we could see. So that's the density and that's the magnetization. You see, it's not ideal. And essentially what happens in this system is that you still have a bending. So this is an iso-m line. So you still have a bending of the critical temperature, but it's very small. And so we use that to estimate how large in size we should go to be able to observe this. And it works, order of magnitude wise, but it doesn't give you anything precise.
I think in the paper it was said that in microscopic models the simulation was not found yet, right?
Was not. So we got it for the activism model, not for the Vicek model. And for the Vicek model, Daniel Sussman got it. I don't know if it's earlier this year or last year. They have something that they call non-reciprocal Voronoi something. What they mean by non-reciprocal is that when you look at your alignment term, if when I align with my neighbors, sorry, I can align with this, or I can align with this. And because my number of neighbors is not necessarily your number of neighbors, this they call non-reciprocal, and this they call reciprocal, or something like that. And in this model, which is the one we simulate with the Vicek walls, they saw the band. So they have it, and it's confirmed now. But indeed, we failed. We were using Seagull, which is a library of applied mass that's allegedly very powerful to simulate Voronoi models. Then we contacted them because we had problem with rectangular boxes, and they told us, oh, there is a bug in the rectangular code. I was like, oh, wait, it's not written anywhere. So at some point we started to be a bit worried. So we're happy to find this band, but yeah, we stopped. Well, then Daniel has developed his own self-propelled Voronoi model, which is on GPU and much more efficient. So never use anyone else's code. Any other question?
Well, then thanks for
2 minutes only.